The mission of the IETF is to make the Internet work better by producing high-quality, relevant technical documents that influence the way people design, use, and manage the Internet. The Internet Task Force initiated in 1994 the design and development of a suite of protocols and standards now known as Internet Protocol version 6 as a worthy tool to phase out and supplant IPv4 over the coming years. The explosive rate of people all over the world connecting to the Internet and the astounding number of new devices that are getting connected every day have led us to a threshold. IPv4 addresses are running out. This table shows a statistic demonstrating how quickly the address space has been getting consumed over the years after 1981, when IPv4 protocol was published. ICANN was formed in 1998. It is a not-for-profit partnership of people from all over the world dedicated to keeping the Internet secure, stable, and interoperable. It promotes competition and develops policy on the Internet's unique identifiers. ICANN commissioned a working group to focus on tasks with other stakeholders to ensure that all the necessary work be done by the Internet community to achieve the continued stable network and service provisions for all users during the IPv4 to v6 migration. IPv6 uses a 128-bit address size compared with the 32-bit system used in IPv4 and will allow for as many as 3.4 times 1038 possible addresses, enough to cover every inhabitant on Earth several times over. The massive proliferation of devices, need for newer and more demanding applications on a global level, and the increasing role of networks in the way business is conducted are some of the pressing issues that IPv6 protocol seeks to cater to. The availability of an almost unlimited number of IP addresses is the most compelling benefit of implementing IPv6 Internet Protocol. Although the increase in the number of bits in the IPv6 address results in an increase in IPv6 header size, the IPv6 header format is simpler. The availability of a very large addressing space and network prefixes provides a flexible network architecture. IPv6 supports existing interior gateway protocols and exterior gateway protocols. The address auto configuration features is built into the IPv6 protocol to facilitate intranet-wide address management. With the availability of a large number of IPv6 addresses to provide globally unique IP addresses for all IP devices, there is no need for NAT. IPsec is mandatory in IPv6 and is part of the IPv6 protocol suite, potentially making the network more secure. IPv6 mobility is built in, and any IPv6 node can use mobility as needed. IPv6 multicast allows IP packets such as video streams to be sent to multiple destinations at the same time, saving network bandwidth. Quality of service is given a special boost in the IPv6 protocol with IPv6 header containing a new field called flow label field that defines how particular packets are identified and handled by your routers. IPv6 header includes the following fields: version, class of traffic, flow label, payload length, next header, hop limit, source IPv6 addresses, and destination IPv6 addresses. All extension headers are processed by the destination node only. Packets are dropped if any header isn't recognized, except for hop-by-hop options. The IPv6 addressing scheme has been designed to provide capability and interoperability with existing IPv4 network architecture. IPv6 processed a larger 128-bit and the use of colons to separate its 16-bit hexadecimal entries. This table summarizes the different IPv6 address types, prefix notations, and uses. Cisco favors a transition strategy from IPv4 to IPv6 that begins from the edges of the network and moves in toward the core. This strategy allows you to control deployment costs and to focus on the needs of the applications. IPv6 forum members have taken a leading role in the definition and implementation of the IPv6 architecture within the IETF and continues to lead the industry efforts for standardization.